Okay, hello everybody, and welcome back to Real Analysis. First, before I jump into the material, I just want to apologize for having missed so many in-class classes. What can I say? COVID-19 stinks. And so, I said the easiest way to do it, instead of trying to try and manage a bunch of sort of synchronous, everybody coming into class by Zoom, during a week where I'm going to be fairly sick, honestly. I decided that the best option would be to just have these pre-made videos and then give you all the opportunity to ask me any questions you might have from the videos. So with that in mind, though, just because it's a video, we're not in person, doesn't mean we don't have a joke of the day. So, 2 lines are outside and suddenly it starts raining. What should those lines do? Well, 2 lines are caught out in the rain. Clearly, they should coincide. Anyways, so when we left off, so it's probably going to be a little bit, I don't know how long this video is going to be. We'll find out together. Excuse me. So last time in class, my 2 sections of real analysis had left off at different points. One had proven part A of the Archimedean property, and one had not. So we'll go back over the proof together, and those who've already seen this proof of part A, well, here's your chance to kind of see it again, just to maybe clarify it a little bit, hopefully. So, Archimedean property is going to say 2 things. First, in part A, it says that given any real number x, there's going to exist some natural number greater than x. Or if you recall, the natural numbers are numbers like 1, 2, 3, 4, 5, the positive integers. So in other words, part A says that the natural numbers as a subset of the reals is unbounded above. Meaning natural numbers will get infinitely large, extend out to the right forever. There is no upper bound for the natural numbers within the reals. And part B says something somewhat similar. It says given any positive real number y, there's going to exist some natural number n such that 1 over n is less than y. And again, as a reminder, st, if you ever see me write that, that just means such that. So, we talked a little bit about part A in both sections. And we said that Dr. Gerstle, this feels like a big, fat duh. I think Conrad and Lionel both gave this a 1 out of 10 in terms of where 1 is like most obvious thing ever. It's maybe intuitively obvious to you. Why are the natural numbers unbounded above as a subset of the reals? But it's not something that's immediately evident from our axioms. Or if you recall, we have our field axioms, we have our order axioms, and we also have our axiom of completeness, the one that said, given any subset of the reals that's bounded above, it has to have a least upper bound. So let's look at our proof of part A here. Given any real number x, there exists some natural number n such that n is greater than x. So in other words, you give me an x, and no matter how big an x you give me, I should be able to produce some natural number n that's going to be bigger than it. So if you give me 5,769,245.1, I should be able to say 900 billion. Boom, that's a natural number that's greater than what you gave me. And no matter how big a real number you gave me, I should always be able to produce a natural number greater than it. So we're going to prove this with using the same technique we did to prove that square root of 2 is irrational, in that we're going to use reductio ad absurdum, or proof by contradiction. Where proof by contradiction, we're going to assume the opposite of what we'd like to show, namely that you can give me some real number x that I can't produce a natural number greater than. Yet you can give me something that I can't create a natural number for. And we'll show that if that's the case, a contradiction is going to occur somewhere along the way. So here's going to be where we assume the opposite of what we want to prove. We're going to say that suppose natural numbers is bounded above. Meaning there's some real number that's greater than every natural number. Well, with that in mind, And now I'm going to use the axiom of completeness, or again, we're assuming the axiom of completeness for the rest of the semester. So we can say then, by the axiom of completeness, no, AOC doesn't refer to any Congress people. Put down your pitchfork. Put down your pitchfork, Carl. So by the axiom of completeness, we can say that n must have a least upper bound. And I'm going to call it alpha, and say that that is going to be the supremum of the natural numbers. Or if you recall, sup n, or the supremum of n, is just a fancier way of saying the least upper bound of n. Right? Because any subset of the reals that's bounded above has to have a least upper bound, according to the axiom of completeness. So if the natural numbers is a set that's happens to be bounded above, it has to have a least upper bound, like any other bounded above subset of the reals. So alpha is going to be our least upper bound in the natural numbers. And now I'm going to say that since alpha is the supremum, it's the least upper bound of the natural numbers, we know alpha minus 1 is not an upper bound for the natural numbers. Make sure my video is still running. Okay, good. So why is that the case? Well, if alpha is the smallest out of all the upper bounds, alpha minus 1 is clearly some real number that's smaller than alpha. And alpha itself is the smallest out of all the upper bounds for n. Anything less than alpha, such as alpha minus 1, can't possibly be an upper bound for the natural numbers. So alpha minus 1 is not an upper bound for natural numbers. So what does that mean? If we say that alpha minus 1 is not a natural number. Well, that's going to tell us that then there must exist some little lowercase natural number n, some element little n in the set of natural numbers, such that alpha minus 1 is strictly less than n. So why is that? Well, if alpha minus 1 is not an upper bound for the n, if alpha minus 1, in other words, is not greater than every single natural number, then it would have to be the case that there's at least one natural number that's not strictly less than alpha minus 1, and we can just call that one n. So alpha minus 1 has to be less than some natural number n, and then I'm just going to add 1 to both sides of this inequality. We have an order axiom that tells us we can do that, and say thus alpha is less than n plus 1. If you notice, I cited the axiom of completeness when I used it. I didn't cite order axiom number 3, I think it was, when I said because alpha minus 1 is less than n, thus alpha is less than n plus 1, because that feels kind of, that would be going a little bit overboard, trying to cite each order axiom or each field axiom when we use it. So I'm not going to cite like specific field and order axioms and just kind of mention offhand that, oh, this happens because of some order axiom. So now, what do we know? Well, we know that alpha is an upper bound for the natural numbers, and we have some natural number little n such that alpha is less than n plus 1. And I think we have a contradiction here. The idea being alpha is supposed to be bigger, or at least not smaller than every natural number, but here's a natural number, n plus 1, that alpha is not bigger than. In fact, alpha is strictly less than n plus 1. That is going to be our logical contradiction. So writing that down, we can say, however, since little n is a natural number, we know that little n plus 1 is a natural number as well. This implies alpha cannot be an upper bound for the set of natural numbers as alpha is less than a natural number that is n plus 1. And this gives us a contradiction. And we can conclude our proof then by saying thus, n must be unbounded above. Unbounded above. There's our proof. Once again, a proof by contradiction. Excuse me. Where we started by assuming the opposite of what we want to show. We want to show n is unbounded above, so we start by assuming it's bounded above. Then showed that alpha, which is the least upper bound of n, and keeping in mind that a least upper bound still has to be an upper bound, even if alpha is the least upper bound of n, it can't be an upper bound for n, which clearly a logical contradiction. It's an upper bound, it should be an upper bound. So that tells us that the natural numbers go on forever. So I'm going to talk a little bit about the structure of this proof. If you notice, and maybe this is not how you've seen proofs written in the past, depending on which courses you've taken, I wrote everything in terms of complete sentences. So all of these are sentences. Then by the axiom of choice, comma, natural numbers must have a least upper bound, alpha equals the supremum of n. Since alpha equals blah, we know blah is not an upper bound for n. Everything is a sentence here. And when you're writing your proofs, I want you to get used to writing them in complete sentences as well. Don't just say things like, by AOC, alpha equals sup of n. Alpha minus 1 equals not an upper bound. Alpha minus 1 less than n. Alpha less than n plus 1. It's important when writing a proof to kind of make it readable, just like how you would make an English paper, a history paper readable. And thus you include sort of these connected words like since, therefore, then, suppose, then by, blah, axiom. So try and get in that habit as you're writing these proofs. So that's it for part A. Let's look at part B of this theory, which says, given any positive real number y, there always exists some natural number n such that 1 over n is less than y. And what I would like for you to do is I want you to pause the video for a minute here and see if you can try and sketch a proof of what might a proof of this property look like. And I'll give you a hint. See if you can use part A to help you prove part B. All right, pause the video. Action pose. Action pose in. So, Laurie, what do you think? Well, Laurie has suggested that we start by letting y be some real number greater than 0. You should have paused the video by now, by the way. Which is a good idea, Laurie. Just start by defining the variable we're going to use. So we're going to say let y be greater than 0. And if we don't write anything else, when we say something like let y be greater than 0, we assume y can be an arbitrary real number. Technically, I could say let y be in the set of all real numbers such that y is greater than 0. But if we just say let y greater than 0, that says the same thing. Surprised you felt the need, Laurie, to correct me on that. So we let y be greater than 0, and we want to find some natural number n such that 1 over n is less than y. So what I'm going to do something a little bit sneaky. I'm going to then say let x be equal to 1 over y. So here, I'm using the fact that every real number has a multiplicative inverse, meaning you can always take 1 divided by any real number other than 0, and that's not an issue here since y is strictly greater than 0. So I'm going to define a new variable x and just say let x be equal to 1 over y. And with that, I'm going to say by part A, x is some real number. Therefore, there exists some natural number greater than x. So then, by part A, we know there exists some natural number n such that n is greater than x. We just proved that. That has to happen given any real number x. So I'm using that result. So now we know that n is greater than 1 over x. So I claim we can say that since n is greater than x, 1 over n should be less than 1 over x. And that's something we didn't prove, but that's sort of something you can prove from the order axioms. That if you have two positive real numbers, say n and x, and n is greater than x, you can sort of take the multiplicative inverse of each side, swap it to 1 over n and 1 over x, and then the greater than turns into a less than, and vice versa. Similar to how saying things like 3 may be bigger than 2, but 1/2 is bigger than 1/3. So 1 over n is less than 1 over x. But what is 1 over x? Well, 1 over x, we know, is equal to 1 divided by 1 over y. And 1 over y is just going to be y. Thus, 1 over n is less than y. We've shown that given any real number, or positive real number y to start with, we could produce some natural number, n, that is going to make 1 over n less than y. Because 1 over n is less than thing, which is equal to thing, which is equal to y. That means 1 over n has to be strictly less than y. Oh, and as I mentioned before, I like putting these little squares at the end of my proofs to indicate that proof complete. So you may have noticed, in proving part B here, I did something interesting. I know, who's someone I can pick on? Adam's jumping up and down the seat asking, Dr. Gersel, is there a right for you to just use this result of part A in the middle of your proof without having to reprove it? And I would argue that's totally okay because we already proved part A over here. Once we prove something in class, we don't have, unless the question specifically says to reprove it, on like an in-class exam or something, once we prove something in class, we don't have to reprove it. We could just keep, once we've shown that this result has to be true, we can just use that as a fact for the rest of the semester. And so part B was actually proved using part A, so we can say B is a corollary to part A, where corollary is basically a result that can be proved using some other result fairly quickly. So in this case, our proof of part A was fairly long, but once we had part A, our proof of part B was pretty quick, just using part A as sort of like our big stepping stone to help us prove part B. Yeah, so now that we've proven both parts A and B, we can just use these as facts for the rest of the semester. Again, unless I give you like an example question or something that says specifically, prove this statement. You can't just say, oh, it's proved in class, done. I'll throw my chalk at you if you do that. I'm not actually going to throw my chalk at the camera hanging up on this one because I worry I'd actually hit it. My aim's not that good. Anyways, what do we care about this? Well, if you recall, we said something in class last time about the nice property that the rational numbers have in comparison to the real numbers, which is that the rational numbers are dense in the real numbers. And what that means is if I take any interval of real numbers, give me any two real numbers, no matter how close they are, whether it's say pi and pi plus 1 over a trillion, no matter how close the two real numbers you give me are, no matter how close they are to each other, I can always find some rational number, a number that can be written as a fraction of integers. I can always find some rational number that lies in between those two real numbers. So let's actually prove this. This is our density of the rationals theorem. I'm going to erase this part. Because we're going to need our Archimedean property in order to be able to prove this. Oh man, probably maybe see why I didn't want to do this in person. Let's spend the whole class sneezing all over y'all. So the density property of the rationals is going to say that given any two real numbers, a and b, with a less than b, there exists some rational number r there exists some rational number r such that a is less than r is less than b. So in other words, anywhere you see a real number, there's a rational number that's going to be very close to it. Because given no matter how small an interval of real numbers you give me, I should always be able to produce some rational number that can squeeze inside of that interval, strictly in between a and b. So let's see if we can prove this. So proof, I'm going to start off by just saying let a and b be real numbers with a strictly less than b. In other words, I'm defining the variables that we're going to be using for the rest of the problem. I'm going to do something maybe a little bit unorthodox here, and I'm going to say by the Archimedean property, part A, in other words, by this result right here, we know something about A and B. There must exist some natural number n such that 1 over n is less than b minus a. Oh, wait, that shouldn't, all right, sorry. We're using part B of the Archimedean property, this one, that says, given any positive real number, and if a and b are positive, and if a and b are any two real numbers where a is less than b, b minus a is always going to be positive, because it's just the difference between the two. So b minus a is some positive real number, and according to part B of the Archimedean property, given any positive real number, I should always be able to produce a natural number n with 1 over n less than that positive real number. So since b minus a is a positive real number, put that greater than 0 down here, we should be able to find natural number n with 1 over n less than b minus a. Now you have to think to yourselves, Dr. Gerstle, why would you choose 1 over n less than b minus a? Why not just b or a? And my answer to you is, it may not make sense at first why I wanted some 1 over n to be less than b minus a. But hold on to your hats, because this is going to be an interesting ride. So, first of all, I'm going to say that since 1 over n is less than b minus a, that's going to tell us that a is less than b minus 1 over n. And to get that, you could just add a to both sides of this inequality, and then subtract 1 over n from both sides of this inequality. And that doesn't change the sign. You're adding and subtracting the same thing from both sides. Again, that was one of our order axioms, but I'm not going to cite which one because that's just unnecessary. So since 1 over n is less than b minus a, adding a to both sides and subtracting 1 over n from both sides gives us that a is less than b minus 1 over n. And that's going to be important. So now, what I'm going to do is I'm going to pick a natural number n such that m minus 1 is less than or equal to n times a, which is strictly less than m. And so you might be thinking to yourself, Dr. Gerstle, what the heck are you doing? How do you know we can do something like that? Well, essentially, what I'm doing is I'm not explicitly stating it, but I'm using part A of the Archimedean property to say n is a natural number. A is some real number, maybe natural, it may be not, it may be rational, it may be irrational. And if we look at a number line here, n times a is going to be somewhere on the number line. And here, I'm using the fact that the natural numbers are unbounded above. They extend forever to the right to essentially say that, let's say this is 1, this is 2, this is 3, this is 4, this is 5, etc., etc. We know NA has to lie between two different natural numbers. And so the natural number that NA lies in between, this one, 5, I'm just going to call M, which would make this one 4 equal to M minus 1. I'm basically saying we have some real positive real number, pick the two natural numbers that lies in between. And we have to have a less than or equal to sign here, because if n times a is a natural number, then we might just have to set it equal to n minus 1. So I hope that makes sense. So we've picked a natural number m, and we want to specifically pick the one that makes n times a lie in between m minus 1 and m. And so now, what do we want to do, Dr. Gerstel? We want to find some rational number r that's in between a and b. And it's going to turn out that the rational number r that we're going to use is m divided by n. So let's see if we can prove that m divided by n has to be strictly in between a and b. Well, first of all, if we just use this right half, the fact that NA is less than m, we can immediately say that since n times a is less than m, and n is greater than 0, because all natural numbers are positive, we can divide both sides of this inequality by n to get a is less than m over n. That's basically divided both sides by n here. So that's one of the two things we wanted, that m over n is strictly greater than a. We also need to show that it's strictly less than b. And to do that, it's going to involve a little more work. So what I'm going to say is that since m minus 1 is less than or equal to n times a, we know by adding 1 to both sides of this inequality that m has to be less than or equal to na plus 1. Why? Well, if we add 1, then both sides, and then the inequality doesn't change. That's an order axiom. Now, I'm going to use the fact that a is strictly less than b minus 1 over n to say that n times a plus 1 is going to be strictly less than n times b minus 1 over n plus 1. So basically, I'm using this property of a to say that a is less than b minus 1 over n, to say that if we take na plus 1, that has to be strictly less than n times this expression a is less than plus 1. So what do we know, though, about n times the quantity b minus 1 over n plus 1? Well, if we use the distributive property, which is one of our field axioms, to multiply this out, FOIL this out, we'll get n times b minus n over n plus 1. But minus n over n is just going to be minus 1 plus 1, which is going to be equal to n times b. And what do we know? We know that n is strictly less than boop, is less than or equal to boop, which is strictly less than bop, which is equal to black, which is equal to blop, which is equal to n times b. So n is strictly less than n times b, because we have a string of less than or equal tos, and less thans, with at least one strict less than in there. So n is strictly less than n times b. And thus, here's our last step. I'm just going to divide both sides by n. n divided by n is less than b. And that was the other thing we needed to prove. We showed that m over n has to be strictly greater than a and strictly less than b. Thus, you can say m over n is a rational number. Rational because m and n are both natural numbers and thus integers. And integer divided by integer is definition of what a rational number is. Thus, m over n is a rational number such that a is less than m over n is less than b, and we're done. We found the thing we wanted. We showed that no matter how close a and b are to each other, there's always some rational number in between. So if you gave me, say, two very, very close real numbers, like square root of 2 and square root of 2 plus 1 over 999,999. These are two real numbers. According to this density property, we should be able to find some rational number that lies strictly in between. Strictly greater than square root of 2, strictly less than square root of 2 plus 1 over 9. Don't ask me to actually find one for these two specific numbers, because that would be tedious and annoying. But according to what our theorem that we just proved, we should be able to do that. And so, due to this property, we say that Q is dense in R. So let's just write that down. The fact that between any two real numbers there exists a rational number, we can say that since this property holds true, Q is dense in R. And here, when you see the word dense, what I want you to be thinking of is sort of like in science, the idea of density. If you have some material with a very high density in, say, a chemistry class, that means that all your atoms in that substance are going to be packed really close together. They're all packed super tight. It's a very dense sort of substance. So when we say something like Q is dense in R, what that means is that all the real numbers, that all the rational numbers are packed very tightly within the reals. So that if you take, no matter how close together you take those two real numbers, you're always going to get some rational in there. So their rationals are packed very tightly in the reals. Thus the word dense, or density. So what does that mean? So that kind of implies that would seem to imply that, well, if between any two real numbers, no matter how close, you always get a rational number. And by the way, on homework 2, I asked you to prove that not only there has to be at least one rational number, but there has to be infinitely many between any two reals. You might want to say, Dr. Ursel, I would suspect from this that means almost every single real number is a rational number, because the rational numbers are so packed in tightly within the set of reals. No matter what reals you take, you can always find infinitely many rationals in between. And you would be. And intuition might seem to make that a little bit, you might make that claim based off your intuition, that, the fact that the rationals are packed in so tightly to the reals means that almost every real number is rational. It's going to turn out, though, that that's not the case. In fact, as we're going to see in the next packet, almost every single real number is not rational. But before we do that, let's see if we can prove the same property, the density of the rationals in the reals, and let's see if we can actually prove that the irrationals are also dense within the set of all real numbers. So I'm going to define a new set here, which is the set of all irrational numbers, which is it's a set of all real numbers that are not rational. So the set of all real numbers x satisfying the property that x is not an element of Q. A set of all real numbers that are not elements of the rationals. So some things in this set, we're going to call this set, by the way, I. Part of why we didn't use I for the integers is because I is going to be reserved for irrational numbers. So some numbers that would be in this set would be things like square root of 2, pi, e, real numbers that are not rational, that can't be written as a fraction of integers. And I'm going to write this down as sort of a theorem and say that the irrational numbers I is dense in the set of all real numbers, i.e. between any a comma b in the real numbers. Let me rewrite that a little bit. I'm going to say instead, if a and b are any two real numbers with a less than b, there exists some real number x, or irrational number x, such that x is strictly in between a and b. So between any two real numbers, not only is there going to have to exist at least one rational number, and in fact infinitely many, there's also going to have to exist at least one irrational number as well. In fact, infinitely many of those as well. So let's see if we can prove this. And our proof is actually going to use the density of the rationals to prove the density of the irrationals, which is kind of fun. So to start with, it's going to be our proof. So here is the theorem that we're proving, that the irrationals are dense within the set of all reals. So our proof, to start off with, we're going to say let a and b be any two real numbers with a less than b. In other words, we're defining our variables that we're working with. And we want to prove that we can find some irrational number between a and b. And I'm going to say that then, if a and b are real numbers with a less than b, then a plus square root of 2 and b plus square root of 2 are real numbers, with a plus square root of 2 being less than b plus square root of 2. So why square root of 2? Well, square root of 2 is something we know is irrational, which is going to be important later on. And here I'm using a couple properties. First, I'm using the closure of the real numbers under addition, which is, I think, our first real axiom. To say if a is a real number and square root of 2 is a real number, then their sum, a plus square root of 2, has to be a real number, and ditto with b plus square root of 2. I'm also using order axiom to say if a is less than b, then a plus root 2 is less than b plus root 2. So we know that a plus root 2 is less than b plus root 2. And now I'm going to use the density of the rational numbers to say a plus root 2 and b plus root 2 are two real numbers. One is less than the other. Therefore, there should exist some rational number in between a plus root 2 and b plus root 2. So then, by the density of irrational numbers in R, in other words, I'm using this result right here, there exists some m divided by n in Q with a plus root 2 less than m over n less than b plus root 2. So essentially what I'm doing is I'm just using this result here, that between any two reals there's a rational number, and we're just replacing a and b in this statement with a plus root 2 and b plus root 2. Since a plus root 2 is less than b plus root 2, there has to exist some rational number in between by this result over here. So we know a plus root 2 is strictly less than m over n, strictly less than b plus root 2. I'm going to subtract root 2 from each side of this double inequality to say that a is going to be less than m over n minus root 2, is strictly less than b. So if we subtract root 2 here, subtract root 2 here, subtract root 2 here, we'll be left with m over n minus root 2 has to be strictly between a and b. And here I claim is going to be our x that we're looking for, our irrational number stuck between a and b. So let's ask this question. Why is m over n minus root 2 going to be an irrational number? Well, here's the thing. M over n is a rational number, Root 2 is very much an irrational number. Anytime you add a rational number and an irrational number together, you're always going to get something irrational. And we'll see that, and we can actually say that very quickly as sort of a quick proof by contradiction here within our overall proof. We can say that, for instance, note that m over n minus root 2 is not an element of the rationals. And why is that? Because otherwise, we have that m over n minus root 2, m over n minus that. If we take m over n and subtract off m over n minus root 2, what are we going to get? Well, it turns out we're going to get square root of 2. But this m over n would be an element in the rationals. That we assumed early on. We're assuming that m over n minus root 2 is rational for the purpose of our sort of mini proof by contradiction. So this thing would be assumed to be a rational number q. And what do we know if we take a rational number and subtract off another rational number? What's that, Allie? Allie says that if we take two rational numbers and subtract, we'll always get a rational number. In fact, that's number 1 on your homework, I think. Homework 2. So we would get that the difference, square root of 2, would have to be in q. But square root of 2 is not in q. We know that from a week ago. That radical 2, square root of 2, is not a rational number. A contradiction. And thus, what we can say is that if we let x be equal to m over n minus root 2, then x is an irrational number, because we just showed that this number is a real number that can't possibly be rational. So x and I, and x is strictly in between a and b, because m over n minus root 2 is strictly in between a and b, as decided. So what's that tell us? Well, it's going to tell us something interesting. It's going to tell us that give me any two real numbers. It doesn't matter how close they are to each other. Say like pi and pi plus 1 over a billion again. I should not only be able to find a rational number between those two real numbers, I should also be able to find an irrational number. And from there, you can actually prove, again, which you will do on your next homework, you actually prove that if there's always at least one rational number between a and b, there have to be infinitely many. And if there's at least one irrational number between a and b always, there have to be infinitely many. That is some gnarly stuff, if you ask me. So, what's that say? Does that actually tell us anything about how many irrational numbers there are to how many rational numbers there are? They're both digs in the reals. So, are there going to be an equal number of rationals and irrationals? Turns out the answer is no. In fact, we're going to show later on that even though the rationals are dense within the reals, there's way, way, way more irrational numbers out there than there are rational numbers floating around the world. But that we're going to see in a future class. So I think that's going to do it for this packet and for this video. When we come back next time, we're going to start talking about how you can compare the size of two sets using the idea of one-to-one and onto functions. And you might say, oh, Dr. Herzl, it's easy to compare two sets. This one has 4 elements, this one has 6 elements. One with 6 elements has more. Okay, yeah, sure. How can we compare two sets when they're infinitely big? We're going to find a way to do that. So I hope you all are doing okay. Hope you all are staying healthier than me. See you all around. Take care. Stay healthy, stay safe, stay awesome. Thumbs up to you, Lily.